For years, driving an electric car in extreme cold was a true test of patience and planning. The promise of silent range and energy efficiency was often dashed as soon as the temperature dropped below freezing. Lithium-ion batteries, which dominate the market to this day, simply weren't designed to handle harsh winters. All it took was parking your car on a freezing night to wake up with 20% of the battery life gone, even without having driven a single kilometer. The chemical reaction slows, the electrolyte thickens, and the ions crawl as if trying to cross a frozen lake. And the worst part? This happens even in the most expensive cars. Anyone living in regions like Minnesota, Alaska, or northern Canada knows this scenario all too well. Range plummets, sometimes by half, and drivers end up hostage to the charger. Planning the route becomes almost a military operation. Where to stop, how long to charge, how to conserve every last bit of battery until they get home. For many, this means leaving 30 minutes early just to ensure their car survives the daily commute. It's a problem that affects vehicle confidence, routine, and, ultimately, the very idea of freedom a car should offer. But what changes when the aluminum-ion battery enters the picture? This is where things get interesting. This technology uses an ionic gel electrolyte, and the rule-breaking detail is that it remains fluid down to 60 grados Celsius. This means that even with the thermometer registering polar temperatures, the ion flow remains virtually intact. The result? A loss of range so small that it seems laughable compared to the drastic drops in lithium. Instead of losing 40%, the driver sees a maximum of 5% disappear. And that's enough to transform the winter experience. This type of battery doesn't go into hibernation mode like lithium-ion batteries. It continues to function almost as if it were a spring day. Drivers don't need to warm up the car for 20 minutes before leaving or cross their fingers that the system won't crash. The power is there, available, no tricks. This means waking up, turning the key, or pressing the button, and driving away as if nothing had happened. It's not a luxury. It's the basics finally being delivered, as they should be. This more stable behavior translates into confidence. No one needs to be glued to weather apps anymore to see if their car will make it through the next day. There's no longer the constant anxiety of being tethered to an outlet, nor the fear of being stranded on the road due to unexpected cold. Aluminum technology simply removes these variables from the equation. And this changes everything for those who rely on their cars daily, in regions where winter lasts more than 3 months. And it's not just about driving. The idea that electric cars require constant attention loses its power with this new type of battery. You can leave it parked for days in sub-zero temperatures without experiencing significant battery loss. You can even travel and leave the car at the airport without worrying about whether it will start up when you get back. It's a freedom that only those who have endured the suffocation of a harsh winter truly understand the value of. Furthermore, the impact goes beyond personal use. Fleets of taxis, delivery vehicles, and even school buses in cold regions can operate with much more predictability and lower costs. The savings in energy, maintenance, and time lost with emergency charging begin to add up quickly. And all this without having to reinvent the vehicle. It's the battery that makes the magic happen. If there's one thing that frustrates any electric car owner, it's realizing that, in addition to the loss of range in cold weather, charging also becomes a soap opera. With lithium-ion batteries, what would normally take 30 minutes can exceed an hour, depending on how cold the morning is. And it's not just slowness. Intense cold can damage the battery's internal cells, creating metallic deposits on the anode, a process known as plating, which compromises battery performance and lifespan. It's as if every recharge in sub-zero temperatures is a silent Russian roulette, where you never know when the battery will start to fail for good. Enter aluminum, and with it, another twist. Unlike lithium, aluminum ions don't suffer from this plating. They dissolve completely in the salt-based electrolyte, without accumulating in the wrong places or causing short circuits. This allows the battery to be charged under extreme conditions without compromising its integrity. And when it comes to efficiency, the number is impressive. Even at 22 degrees Celsius, a full charge from 0 to 100% can be achieved in about 10 minutes. For those who live on the go, this completely changes the relationship with their car. Picture the scene. It's snowing outside, everything is white, and the thermometer is registering sub-zero temperatures. While neighbors are still scraping their windshields or waiting for the car's heater to come on, the driver of the Tesla with the aluminum battery is ready to go. In less time than it takes to make a cup of coffee, the car is fully charged and has intact range. And this isn't an optimistic or idealized scenario. It's what real-world testing already shows as a reliable trend. Another interesting point is that this charging speed doesn't require any futuristic infrastructure. Existing fast charging stations can be used, with the advantage that the aluminum battery requires less thermal compensation. This means less energy spent on heaters and less waste during the process. In practice, the driver pays less for the same energy and also saves time. The bill is paid faster than the charging itself. Furthermore, there's no constant risk of overheating during charging, even under extreme conditions. Aluminum batteries generate less residual heat and handle thermal dissipation better. This allows the system to operate safely, even when pushed to its limits. No dashboard alerts, no unpleasant surprises, and no need to monitor the charge like a ticking time bomb. Anyone who drives for work knows how valuable this is. App-based drivers, delivery fleets, and even emergency services can't afford to wait an hour to recharge. The difference between 10 minutes and 60 minutes is literally the difference between keeping the business running and losing money. And when this efficiency remains consistent, come rain or shine, the benefits accumulate day after day. It's worth remembering that environmental impact also comes into play. With less wasted energy, fewer auxiliary systems running, and a more efficient charging cycle, the use of aluminum batteries contributes to an even smaller carbon footprint. In other words, besides being more practical for the driver, it's more sustainable for the planet. And at this point, even those who aren't particularly interested in ecology end up realizing that the choice makes sense. If cold used to be a silent villain for electric car batteries, heat has never been a reliable ally either. On intense summer days, especially in desert regions or urban areas with boiling asphalt, extreme heat can turn a simple trip into a technical hazard. Lithium-ion batteries are sensitive to high temperatures, and when exposed to temperatures above 60 degrees, they begin to show worrying symptoms. The liquid electrolyte can decompose, generate flammable gases, and cause the cell to swell, a sign that something seriously wrong is about to happen. And since this doesn't always provide advance warning, the real risk is driving without knowing that the battery is about to fail. The problem becomes even more serious when you understand how heat accumulates. With lithium batteries, even short trips on a very hot day are enough to raise the pack's internal temperature. And there's no point turning on the air conditioning and assuming everything is fine. The battery's cooling system has to work harder, consumes extra energy, and, ironically, reduces the car's range. It's a cycle that undermines efficiency and increases system wear, especially in tropical countries or states like Arizona, Texas, or Nevada, where driving in temperatures of 45 degrees 114 bars is commonplace. Now imagine a battery designed to not only withstand heat, but virtually ignore it. Tesla's aluminum battery is equipped with electrodes and materials that look like they're from an aerospace project. And, in part, they are. The aluminum anode has a melting point above 1,220 degrees or Celsius, 660 degrees Celsius, and the graphene cathode maintains its stable structure even above 900 degrees Celsius. All this combined with the ionic electrolyte, which doesn't evaporate or release flammable gases until temperatures exceed 300 Celsius, 864 degrees. It's as if each cell were protected by an invisible heat shield. But what really stands out about this technology is the graphene's behavior. This material acts like a thermal superhighway, conducting heat so efficiently that it doesn't accumulate in critical points. It's this accelerated conduction that prevents the infamous hot spots, those internal areas of the battery that heat unevenly and can cause localized failures. With the temperature always evenly distributed, the risk of overheating virtually disappears. Tesla went a step further, adopting a honeycomb-shaped internal design for the cells, creating natural ventilation channels that increase thermal dispersion. This hexagonal arrangement allows heat to circulate and escape without the need for additional fans or pumps. And here's another surprising detail. This design choice helps reduce the electrode surface temperature by up to 20% compared to conventional batteries. It's a difference that, in practice, can save the entire system from failures caused by excessive heat. As a direct result, Tesla can completely eliminate the active cooling system in its aluminum battery vehicles. This not only reduces the car's weight, but also cuts approximately $1,800 in production costs per vehicle. What's more, without additional mechanical components, there's less chance of technical failures, less maintenance, and a battery that retains up to 98% of its energy capacity, even on long journeys under blazing sun. This also means that range doesn't evaporate along with the driver's sweat. While cars with lithium batteries can lose up to 20 miles due to heat and cooling system usage, those equipped with aluminum maintain their performance virtually unchanged. The difference is felt in your wallet, safety, and even mental comfort. After all, no one wants to drive with the feeling that the car could overheat at any moment. When it comes to endurance, many people immediately think of heat and cold, but they forget another silent enemy: water. And we're not just talking about driving in moderate rain. Those who live in regions with frequent rainfall or even occasional flooding know that a deep puddle or a flooded street can turn the journey into a minefield. Lithium-ion batteries even promise endurance with certifications like IP67, which guarantee temporary immersion. But these protections have an expiration date. After 2 or 3 years of constant exposure to humidity, acid rain, or salt water, the materials begin to give way, and when water finds its way inside, damage is inevitable. The problem lies in the materials used. Most battery packs use standard aluminum or stamped steel housings with an epoxy coating that appears durable but eventually cracks or swells over time. When exposed to moisture, these cracks allow water to enter, corroding the circuits and creating the risk of short circuits and even fires. The worst part? The damage isn't always immediate. Sometimes the battery functions normally for weeks until a sudden failure interrupts its operation, or worse, triggers a dangerous reaction. It's an invisible risk that increases with each storm. To solve this, Tesla incorporated materials that would normally only be used in aerospace or military applications. The aluminum-ion battery's casing is made from a special aluminum alloy reinforced with 10% titanium, which already offers exceptional corrosion resistance even in highly alkaline or acidic environments. But the innovation goes beyond the metal. Over this structure, a protective layer called hydroshield is applied, a polymer graphene mixture sprayed at 10,000 degrees, forming a nanometer-level waterproof membrane. And the most interesting thing? It's self-healing. Small scratches heal themselves in up to 5 minutes. This outer shielding is just the first line of defense. Each cell inside the battery is encapsulated with a 0.1 mm silicone film that completely surrounds the component, sealing even the smallest gaps where moisture could penetrate. The assembly is precision assembled to ensure that not even salt water or acid rain, with a pH between 4 and 6, can affect the internal systems. And because silicone doesn't dry out over time, this seal remains intact for decades. In tests conducted simulating continuous humid environments for over 1,000 days, Not a single cell exhibited corrosion. In practice, this translates into peace of mind. Drivers don't have to rush to park their car before the storm, nor worry about drying everything afterward. They can weather urban floods 5 to 7 inches deep without fear of short-circuiting. And there's no need to disassemble the car to check for water ingress into the battery. Protection is definitive, as if each cell were isolated by an underwater capsule. For those who live in places like Oregon, Washington, Amazonas, or coastal cities with constant sea air, this durability is gold. Not only does it extend the car's lifespan, but it also eliminates maintenance costs. No more replacing battery modules due to invisible oxidation or circuits compromised by water infiltration. And this makes all the difference in a scenario where the battery is by far the most expensive component of the vehicle. Furthermore, with this waterproofing, the battery maintains its efficiency even over the years. While lithium-ion models begin to suffer performance loss after 5 or 6 years, Tesla's aluminum batteries demonstrate stability above 95% capacity even after a decade of use in humid environments. This extends not only battery life but also the vehicle's resale value, something that interests both end consumers and the fleet market. The combination of structural protection, intelligent materials, and sealing engineering represents a new era for electric cars. The fear that a storm or a flooded street could turn a modern car into a dead weight is becoming a thing of the past. And when technology is designed to last decades, not just a few warranty cycles, it stops being merely a technical differentiator. It becomes a genuine commitment to the driver, who needs to trust the car in any condition, even underwater. After so much resistance to cold, heat, and water, a question arises that everyone asks, but doesn't always find a clear answer. How long will this battery actually last? Because all this robustness is useless if, in the end, its lifespan is the same as that of traditional batteries. The truth is that the lifespan of a lithium-ion battery rarely exceeds 7 years in real use. That is, if it doesn't face extreme weather conditions or charging issues. Over time, it loses capacity, range, and performance. And since replacing a pack can cost up to $20,000, this unexpected expense becomes a nightmare for any electric car owner. Tesla's aluminum-ion battery, on the other hand, was designed with real-world longevity in mind. In laboratory tests and simulated urban and highway use, these batteries demonstrated stability above 90% capacity even after 20 years of continuous use. This means that a car purchased today with this technology could run until 2046 without needing replacement. And it's not just promises. The materials used, such as graphene, titanium aluminum, and ionic electrolytes, simply don't suffer the same cumulative wear and tear as the organic compounds present in lithium batteries. This extended lifespan brings silent but brutally effective savings. When you add up the avoided costs for maintenance, cooling, module replacements, and recalibration, the car owner can save up to $5,000 over 2 decades. What's more, because it maintains near full efficiency even after years of use, the aluminum-ion battery doesn't require software updates to counteract degradation, nor complicated thermal management strategies.